Hello everyone, this is Zhiqi Wang from the Chinese University of Hong Kong. Here I will present our paper, Heracles, an efficient storage model and data flushing for performance monitoring time series. First, I will introduce the background and the motivation. Currently, there are many time series management systems available on the market, including the time series databases like InfluxDB and monitoring systems like Prometheus. For performance monitoring system, we have data collectors periodically scrape data from different kinds of data sources. Storage engine handles the data insertion from the data collectors and user queries from the web interface or HTTP API. For a time series, typically it has two components. The first one is the time series identifier, including metric name and tag pairs. The second part is a series of data points with the timestamp and the metric value. Commonly, the time series are collected in a group manner. For example, the time series from the same machine or container, and they are collected periodically with stable intervals, and the metric value of most time series is rather stable. For the index of time series storage engine, commonly an inverted index is built for each tag pair as shown in the top figure. For the storage of data samples, the design philosophy is similar to LSM tree, where they batch the most recent data in memory block, and after a specific period, for example 2 hours in Prometheus, they are flushed to disk. For data samples of each time series, it is stored independently with compressed chunks. To obtain a high compression ratio, those chunks contain relatively lots of data samples, for example 120 samples in Prometheus. However, the current design suffers from several issues, and the first one is about the storage model. First, the query is inefficient. Before accessing the chunks, it needs to linearly search chunk metadata to locate the chunks with overlapping time ranges. Then for each located chunk, it needs to decompress from the beginning until it finds the targeted sample. The figure shows that Prometheus spends around half of the time to locate the first batch sample. Second, redundant timestamps are stored for those time series from the same source. Besides, an expensive log operation is required for each time series during the insertion. The second issue is on data flushing. We observe high CPU utilization in Prometheus during data flushing that can significantly affect the query performance. The top figure shows the query latency when there's no data flushing, and the bottom figure shows the query performance during data flushing, and you can see the fluctuation is quite intensive. Besides, Prometheus directly discards the in-memory data that can still serve queries after data flushing, which is wasteful. Next, I will introduce our design. In the group model, the timestamps are shared, and the compression is based on a small unit, namely tuple. We separate in-memory data and on-disk data into two models, respectively. For the in-memory model, it is continuously absorbing new data samples. As a result, we attach the offsets at the end of timestamp tuples to make them correctly map to the corresponding metric value tuples. For the on-disk group, data is immutable, thus we use Paddy tuple for better compression ratio. For the timestamp compression, for the in-memory model, we use base delta encoding as shown in the left figure. The first value in a tuple serves as a base, while for the following values, we store the deltas. For the on-disk model, since data are fixed and the time series are collected rather periodically, we can resort to a scaling encoding method as shown in the right figure. We compute the average interval between two samples and store the fluctuation for each value. Through this, we can use much smaller bit widths to store the fluctuation than using deltas. For metric value compression, we base on XOR compression proposed by Facebook Gorilla. The details can be found in the paper. For each value inside a tuple, it is important to choose a base value to perform the XOR operation. For the first value inside a tuple, we consider the first or the median value of the time series in the current time partition. For the following values inside the tuple, we XOR them with the previous value. The bottom figure shows the trade-off that as the tuple size increases, the data size gradually decreases, while the query performance gradually degrades. As a result, in our implementation, we choose 8 for balance. In the original XOR algorithm, we found a local optimal issue that can be further optimized. The basic idea is that there are 3 cases for Gorilla to store the XOR results. The figure shows that we are stuck in case 2 from the second result, and we can see it store many users 0. In our scheme, we will detect whether to jump out from case 2, and you can see from the example, if we jump out for the third result, we can save 40 bits, and the details can be found in the paper. To mitigate the query overhead during data flushing, we utilize a rate limiter to gradually flush data. Meanwhile, we would like to keep those flush data that can still serve querying. As a result, we design our own memory manager for data allocation and reclamation. Currently, we leverage a simple scheme for the physical layout, that is, we chop large memory pages into fixed-size blocks, for example 256 bytes, and the data allocation is based on blocks. For time series data, we partition them based on time ranges and attach a first-level epoch for each partition. This epoch provides data visibility for query threads that the partitions older than the hard release line are invisible. For partitions older than the soft release line, for example 2 hours before, they are moved to the corresponding hot area partitions. For partitions older than the hard release line, for example 6 hours before, they are directly moved to the cooling area. Besides, we will trigger the migration from hot to cooling area and from cooling to recycle area once there's memory shortage. For the hot cooling migration, we select more blocks to migrate from the older hot area partitions. Next, I will show the evaluation results. We implement Heracles based on the storage engine of Prometheus, and the source code can be found on GitHub. The experiments are conducted on the common Linux workstation. For the datasets, we collect the real monitoring data from 10 Debian servers with Prometheus node exporter installed. These monitoring targets are also used in the end-to-end experiments. First, we show the experiment of end-to-end latency. Here we replace Prometheus storage engine with Heracles, and we utilize Prometheus recording rule, the periodical background query task of Prometheus. Here we show the query latency of getting the average CPU usage of all monitoring targets in the last 5 minutes. On average, there's a 12% latency reduction on Heracles. Since the storage engine cannot be pushed to the limit in this experiment, in the following slides, we show the results of directly benchmarking the storage engine. Then we show the insertion performance of the storage engine with the random data and the real data collected from our monitoring targets. For each test run, we increase the number of time series. The throughput of Heracles is at least 2 times of that of Prometheus TSDB. This is because we don't need to search for each time series in the memory data structures one by one. Instead, we just search for a group for the insertion. As a result, we can save lots of log operations. Next, we show the query benchmark where we use the query patterns from TSBS. TSBS is a widely used benchmarking suite for time series databases released by Timescale. In the paper, we have the figures for all query patterns, and here we just show 5A1, which means query data on 5 time series from 8 targets, and do aggregation for every 5 minutes window for total 1 hour. On average, the improvement of Heracles is around 44%. Next, we evaluate the query performance during the data flushing. As shown in the figure, the latency fluctuation of Heracles is much smaller than that of Prometheus TSDB. With Memory Manager, the P99.99 and the max query latencies of Heracles are at least 60% lower than that of Prometheus TSDB during data flushing. That's all for the presentation. Thank you.